Hey guys, tonight we're going to talk about the idea of electric charges, and this is a concept that I'm sure you've talked about it before, and hopefully by the end of the night you'll have a pretty good idea of what's going on in electricity and what electricity actually is. So in order to understand electricity, we actually have to do a really good review of what we learned at the first quarter of the year, which is all about chemistry, and it's really basic stuff, so don't fear if you don't know everything, but you will, trust me. So, quick review, we know electrons are out here in the nucleus, or excuse me, not in the nucleus, but the electron cloud, and they're free floating around, and we know that these guys have a negative charge here. Within the nucleus itself, we have two things. We have the protons, which are positively charged, and we have the neutrons, which have no charge whatsoever. Okay, so in the nucleus we see the protons and the neutrons, and then outside of the nucleus we see the electrons, which are negatively charged. Now, charges you've never really seen this way. This is kind of a new way for us to show it to you. We can look at a positive charge here, and if we were to draw the electric fields, notice that my lines are drawn this way. In other words, my arrows are pointing outwards. If I was to draw something that has a negative charge, my arrows go inwards. And what this does is it helps us explain the idea of opposites attract and like charges repel. So if we look at it now, if I put two charges that are the same, so a positive and a positive by one another, you can see that these lines begin to repel one another and actually bend. This is the electric charge is bending. So we can actually see electric field lines there. On the other hand, look at opposites attract. So you see these lines kind of going this way, and then the negative charge is picking it up right here, going in. And this creates this nice fluid movement, or this nice fluid electric field lines. Something that is really important to the physics behind why we see electric charges move. Real quickly, have you seen this before? Charge can never be created or destroyed. It feels like we've had a law of conservation of something for everything, right? So, just like mass, matter, energy, charge can also not be created or destroyed, but guess what? We're going to transfer it from one object to another. And we kind of see this here in this picture, that this balloon and the hair, there's definitely some interaction between the two. We'll talk about tomorrow specifically what's going on with that. So, before we actually talk about how you transfer a charge, we need to kind of determine two very key vocabulary words: an electrical conductor and an electrical insulator. To begin with, a conductor is a material on which charges move freely. In other words, they can go through it. Let's say here's this, my electric charge goes right through it with no problem whatsoever. These would things be like metal. You can think about the copper wire in actual wiring. Water is a pretty good conductor, especially salt water itself. So metals, waters, these are all very good conductors. The human body itself is a great conductor. Insulators, on the other hand, kind of the opposite. So if I draw my insulator, you can see kind of a charge building up, and then occasionally an insulator, the charge is actually going to make it through, but not nearly as efficiently as up here at the top. So charges don't move freely. Look at things like plastic, wood, glass, foam, cloth, ceramic. All of these are electrical insulators. In other words, charges cannot, keyword cannot, move freely. Pretty easy concept, something that we're going to reinforce with you tomorrow. You look at the example I just gave you, an electrical cord. So over here we have the picture. This is just your typical anything that plugs into a wall. And if you actually peeled apart this, okay, which is made of plastic, which is an electrical insulator, and then inside we have an electrical conductor. And the reason for that is because you wouldn't want to plug in just this straight copper wire into the wall because, well, you'd shock yourself pretty good. And we have the electrical insulator on the outside essentially to protect our hands when we're plugging in these cords. So kind of a combination there of an electrical conductor and electrical insulator working together to ensure you don't shock yourself. Transferring charges can be kind of a tricky situation for kids to remember, but tomorrow we have some awesome demos to help you out with this. So remember, I'm not expecting you to come away being an expert on these three things right here, but I am expecting you to have a general understanding of what goes on with them. And tomorrow, of course, we're going to reinforce that. So three main ways you can transfer a charge, one of them being induction, the next one being conduction, and the last one we'll talk about is friction. So induction, transferring a charge by bringing a charged object near a neutral object without touching it. So really what that's saying is you're bringing something. Okay, so let's look at this this rod right here, which has an overall negative charge. We can kind of see this because it, look at it, it's got nothing but negatives in here. We're bringing it near another object, and in this picture, this another object is this door handle right here. Well, when I bring the object close to it, now key word is near. Okay, I've got them big caps and I'm underlining it. Bringing it near it, but I'm not going to actually touch it. What we do is we induce a charge here on the doorknob, and we see that one half of this doorknob becomes positive and the other half becomes extremely negative, kind of split down the middle here. This is what we call an induction. So the total charge is still neutral. In other words, if we looked at this, I still have 4 positives here and 4 negatives here, so overall that is still neutral, right? But the opposite sides will have opposite charges. In other words, if I focus here just on this, that's positive, this is negative. But overall, as a whole, I know that looks like a mess now, sorry guys, this is still neutrally charged, but we're inducing those two sides to have a charge. Got a great demo with a can with that one tomorrow. Conduction. So it's similar to induction, but now we are going to contact or touch these objects. So you can look at this picture again here. We have our negatively charged rod. And now these negative charges will literally leave this rod and be transferred into the doorknob, leaving the doorknob with a very overall negative charge. In order for this to work really well, we need to have 2 conductors because this thing needs to move freely and this thing needs to accept it. So this can work with an insulator here and a conductor, but if you have 2 conductors, it works very well. So clearly the difference between induction and conduction would be induction you don't actually touch, whereas conduction you are making contact. We can think of static discharge here. Okay, this is a really cool way to explain lightning. What we have with static discharge is the transfer of charge between 2 objects due to the buildup of static electricity. So kind of have an example over here. Here's our big cloud, right? Okay. Well, down here we have Earth, and you'll notice that Earth has an accumulation of positive charges. Earth is known as a really positively charged object. It's a reservoir for these charges, always building up. If the Earth is positively charged, that means that the clouds above the Earth, they're not actually touching, right? But what the Earth does is it induces this charge here. So we see this buildup of negative charges here, and then of course the buildup of positives at the top. Well, if the clouds come too close and the positive charges are enough, all of a sudden we see this jump, this giant jump of charges, and you actually can visibly see that in the form of lightning. So lightning happens when negative charges at the bottom of a storm cloud are attracted to positive charges on the ground. Transferring charge, we can see friction here. 2 objects rub up against each other, leaving electrons build up on one side. This is the classic balloon in the hair. So if you can think of this as, here's the hand here, not necessarily hair, we'll show you that. But if we look at this guy is pretty much overall, he's pretty neutral here, and so is the hand, and neutrally charged. Where if after rubbing it, you'll notice that the negative charges were transferred over to the balloon. All of a sudden we have this accumulation. So with friction, it's similar to conduction, but the key word here is rubbing. This is constant movement back and forth of the 2 objects. You can think about walking across a carpet. When you end up walking across a carpet with socks, the socks accumulate all of these negative charges down here. You go to touch a doorknob, and what happens? Well, static discharge, like we just talked about on the last slide. It's once again that jumping of charges from your hand to that doorknob, if you will. So if you want to look at this, you can. This is pretty goofy, and we will definitely show this to you tomorrow, but it is John Travoltage showing you exactly the movement of electrons. You can go to this website. If you don't want to, you can see it tomorrow, but that's all. Remember, don't be an expert on induction, conduction, and friction, but do have an understanding of those concepts.